All right, so good evening, good afternoon, good morning, wherever you are. I'm very glad to welcome you all, and I'm very thankful on behalf of my team to Professor Kevin GARELLO for kindly accepting our invitation and agreeing to give a talk in this W2S platform webinar series on spintronics. Today it is 92nd talk, so I can't wait really to see 8 more talk at least to hit the century, and hopefully in few weeks, few months, we will hopefully go there. Nevertheless, today is an exciting day. I'm really privileged to have Kevin on board, and really looking forward to a very interesting talk on spin orbit talk, MRAM, basics, technological implementation, and perspectives. I think Kevin is very well known in our community, so really does not need a formal introduction, but there are a couple of young students who may not know. So for their benefit, I like to read a very brief introduction of Kevin. So Dr. Kevin GARELLO is a CA research engineer since June 2020, expert in the field of nanomagnetism and spintronics for magnetic memories. He has graduated his PhD in 2009 at SpinTech, very famous place for spintronics and nanomagnetism. In 2010, he joined as a postdoctoral researcher, as a postdoc in the group of Professor Peter Gambardella, where he contributed to establish for the first time the possibility to use spin orbit talks as a new writing mechanism and demonstrated SOT-MRAM concept. In 2013, he joined ETH Zurich to develop an activity dedicated to SOT characterization and understanding that helped to reveal unexpected physics phenomena arising from SOT systems. In 2016, he joined IMEC in Belgium as a senior scientist in charge of emerging magnetic memory program. Notably, he has demonstrated large-scale integration of SOT-MRAM using CMOS compatible processes and novel manufacturable integration approach that allows to reliably write SOT MTJ cells without the assistance of an external magnetic field. He has co-authored more than 40 high-quality international scientific papers, and he has 12 patents to his credit. So on behalf of my W2S team, Braj, Puspendra, Shakti, Azhar, Swayam, and others, I really express sincere gratitude, Kevin, to join our program. And I just like to tell that during the talk, we usually don't take any questions. So if anybody has question, kindly write in the chat box or raise your hand. At the end of the lecture, we will first have a quick break of 30 seconds to take a group photo. And after that, we will take any questions you have. And we usually take all questions. And I mean, we can have a nice interactions. So with this brief introduction and just mention a few things. Now I hand over everything to Kevin. It's all yours. Looking forward to your lecture. Thank you very much.
Okay, thank you, Subanka, for the kind introduction. Hello, everyone. Good morning, evening, or afternoon, depending on where you are located in the world. And thanks for giving me this opportunity to present a bit the work I did over the past 10 years regarding spin orbit talk MRAM. So today, what I will present you is basically tracking back a bit the history of spin orbit talks and developments which have been done around this to bring it toward more maturity regarding applications. We are still not at the application level, but we see a progress in terms of maturity. And this work that I'm going to present is actually mostly the result of work that I did, carried with Professor Gambardella in ETH Zurich, and later that I conducted in IMEC with the full team of IMEC. So I forgot to acknowledge them in the introduction slide, but there are many contributors to this work that were really key people in order to understand the physics, in order to push for the device fabrication, to evaluate the design possibilities, and so on. So I really want to acknowledge all of them. Okay, so in this talk, I will give you first a kind of general context of MRAM for embedded memories. After what I will go through the main effects which are driving spin orbit talks. Of course, today I cannot go too much into the details, otherwise it would be like a full afternoon lecture, and I'm not sure we are ready for that. And after that, I will go through switching by spin-orbit torques, especially in devices, how we do integrate SOT-MRAM technology, what are the typical device performances and the requirements. And I will finish with some of the progress which have been achieved in the past years and perspectives of where could go spin-orbit torques. Okay, so to start first, what is driving us in magnetism and spintronics is mostly memory application. And the reason for that is that if you look at this typical scheme of the memory hierarchy, you have basically two types of worlds, the embedded and the standalone. So the standalone is what is fabricated off chip, which has not the same constraint as the memories which are fabricated on chip and which are close to the compute unit. So when we are going close to the compute unit, what is driving is the speed and to be able to operate at the frequency of the CPU. When we are going to standalone, what is driving is the density and the cost. Well, the cost is always driving, but in high dense storage, the cost is the most important keyword. And that's, of course, where it's difficult nowadays to introduce MRAM. The hard disk drive is already well established, and now the SSD, so the solid state drives based on NAND flash, are also much more cost effective than any other type of technologies. So all of this to say that if we have an interesting spot, and I will come back on this later, for MRAM application, it's mostly for everything that will operate close to the CPU. And this embedded world is mostly driven nowadays by the CMOS scaling, so the Moore laws, basically. And with Moore laws, basically, this is creating some opportunities for us. So the Moore laws initially was mostly for cost reduction because you reduce the size and you gain amount of devices you can sell on a chip. And also at the same time, it was very important to improve the performances of the transistors in terms of frequency of operation, so typically reaching this famous 2 to 3 gigahertz of operation, and also the voltage to operate these devices. So going down from 2 volt to nowadays 0.7 volts. And if we look at the type of memories which are used here to buffer in between the CPU and the main memory, this is mostly SRAM type of devices, so static random access memories, where you have different class of SRAM. So it's a full zoo of variety, but you have basically two types, the high performance and the high density SRAM, which are going to be dedicated for the L1, so high performance for very fast operation, or high density for a bit more of density. But coming with the scaling race, has appeared also many issues related to the transistor itself, and mostly the fact that we have more and more leakage, even when the transistor is in standby operation. And also, this is accompanied when we are scaling down by frequency saturation and a cost increase, because making smaller and smaller requires much more advanced tools, and this is more and more complex to fabricate, and what was requiring before one step now costs 10 steps and so on. So every time we have a severe increase of the cost of fabrication and more reliability issues because we are densifying the structures. This is costing more energy, so more heating and so on. So that's where introducing the non-volatility, and this was already predicted like 30 years ago, is a need, but it's still not really the case because, of course, CMOS technology is systematically improving, and it's more and more difficult to compete with it. But still, if there is a catch for non-volatile memories and MRAM, it's mostly in this world. And why is MRAM ideal for embedded memories? So first, because it's non-volatile, so it has a bistable state, and it can retain information over a very long period of time. And it is compatible with a CMOS voltage, which is very important because at the end of the day, you have a memory, but you have also what is coming around the memory. This is what we call the periphery. And if you are not compatible with the CMOS voltages, it means that this periphery needs to be made bigger, which is going at the end of the day to be a penalty. So that's one key aspect of MRAM. Then it's also very important that since we are targeting memories which are going to be on embedded memories, they have to be fast. And MRAM is known to be very fast, nanosecond time scale, and that will depend on the family of effects that we are using for the writing. It can be quite dense. In the simplest form, it's a 2-terminal. It can be also 3-terminal, but there we gain density compared to SRAM. And it's also very endurant. So all of these are the requirements to go toward this type of applications. And so by increasing MRAM, introducing MRAM in embedded memories, then this would allow us on the simplest picture to increase the cache size. So this would resolve other problems, which are that in order to buffer the information, since the cache memory is not sufficient, many of the memory is also transferred to the main memory. And this is creating what we call memory wall. So increasing the size of the memory on die would be also a huge benefit to lower the memory wall issue. And then combined with that, we have also a gain of speed, more local processing that can be done, so typically in or near memory computing. And we can also think of simplifying the system architecture. So this would be the benefit of introducing MRAM. Nowadays, MRAM is introduced in one module, which is called eFlash, and which is a small local buffer of memory. So we are talking of MRAM, but what is MRAM? So the first building block of a MRAM is called the magnetic tunnel junction. And this is what I am drawing here. So magnetic tunnel junction is basically a magnetic stack made of two layers, which are ferromagnetic and separated by a thin insulator. So this is a tunnel junction. And depending on the relative orientation between the two ferromagnetic layers, the device is going to have a high resistance state or a low resistance state. So this is known as the tunnel magnetoresistance effect, which is basically a filtering effect. And the typical values of this tunnel magnetoresistance that we call TMR are orders of 100 to 250%. And this is mostly depending on this tunnel barrier. So this means that basically we have a variation between 2 and 3, typically, of the base resistance. So this is looking like quite significant, but if we look and compare to other memories, this is actually quite weak. A transistor is 10 to the 9. A PC RAM or so phase change RAM or aux RAM are 10 to the 4. So here we are 10 to the 2. Just to mention that this is actually another drawback for MRAM. The reading window limits the speed of read or requires a periphery which is more complex in order to read the different states. Now, if we look at the stack itself, as you can see, I've been already drawing various layers. In reality, it's even more complex. We have in total about 20 layers. They are most of them sub-nanometer thickness. We have a lot of different compounds, and all of this is required in order to achieve high-quality stacks, which are compatible with back-end of line processes. So back-end of line is when you finish your process and you need to densify oxide for the metal encapsulation. And these are typically annealings which are going toward 400 Celsius degrees. Okay, in terms of stack, I mentioned there are many types of layers, and each of them has a real importance. So the free layer is the one that is going to store the information and that we can commute with different methods of writing. This is what is going to define a bistable zone, okay, and which is going to say that we have basically a memory, that we can define two states which are staying at zero field. An important thing is that if we look to the projections for industry, we are more interested in getting out-of-plane magnetized systems, and I will come back on this later, because then this is what is the most scalable, so the smallest that we can get in terms of footprint. That brings another complexity, that to obtain PMA, what we are doing is often relying on an effect which is arising from interface. So it's called interface anisotropy. And that this is an effect which is scaling of as a 1/t. So we have this compromise that if we want more anisotropy, we need to make thinner the free layer. If we make thinner the free layer, when we scale down, we lose also retention, because retention is also proportional to the volume. So we have to find here a good compromise or novel solutions. Then the second key point in this type of device is, of course, the tunnel barrier. And to have a good tunnel barrier, so to reach typically this ratio of reading window, we are very dependent on the interface. And nowadays, there is one magical solution, which is cobalt iron boron, MgO cobalt iron boron. This is what is giving the best crystallinity of the MgO and the best tunneling effect. Another metric that is important to keep in mind, which has a lot of importance for application, is the resistance of the tunnel barrier, which is characterized by the resistance area product. So this is something that mostly depends on the thickness of the MgO, and that is going to tell you what is going to be the device resistance at a certain diameter, so at a certain dimension. And this is very important because this is what later is going to tell you how to draw your periphery in order to be able to read such element. And so last, to describe this stack, you can see that now we are coming to the complexity. So we have a free layer that we can commute, and we have a reference layer that is going to be used for referencing the signal. This reference layer, we need to couple it to other layers in order to make sure that this is going to be always remaining in the same direction. So for this, we are using a hard layer, which is usually made of a cobalt platinum material. But here we have a first trick. Cobalt platinum is typically HCC configuration, so 111 orientation, the coffee B, which is required for crystallizing the MgO, is 110. So here we need to introduce a first layer in between the reference, which is the coffee B, and the hard layer, which is the cobalt platinum layer, in order to have a texture breaker. So first to decouple the texture so that one layer is not impacting the other one, and at the same time to obtain a strong pinning or ferromagnetic coupling in between these two layers to make sure that the reference layer is well pinned in a specific direction. And this will be characterized by this pinning field. And then because here we have a ferromagnet which is going to radiate a stray field, what we want to do is also to minimize this stray field so that the free layer is mostly centered on 0. And so for this, we are building what we call RKKY, a SAF, a synthetic antiferromagnet. So we are using RKKY effect, which is going to couple two ferromagnet layers, parallel or anti-parallel, depending on the thickness of this spacer. So in our case, we choose a thickness which gives us a synthetic antiferromagnetic configuration. And this is going to minimize the full stray field which is radiated on the free layer. And this is typically characterized by the offset field. So now we have a device. In terms of magnetic properties, what is important for us is the TMR, so reading window, the coercivity, which is a signature of anisotropy and which gives us the thermal stability somehow. And the offset field, are we well centered? The pinning field, do we have a reference layer which is well pinned, so which is not affected by external conditions? Now, this was mostly for the reading or the building block. Now, how do we write or operate this device? Historically, it was done by a field, so an external field or an embedded field, which is driven by Ørsted. But this is something which has been used in the very first versions of MRAM products, but which nowadays is totally abandoned because this is very costly in terms of energy and density. Then came in 2000 the discovery of spin transfer torque and the first experimental demonstration of this, which led to this spin transfer torque MRAM. So spin transfer torque is basically we inject a current through the device, it gets spin polarized and transfer a spin torque to the other layer. So at the beginning, it's going to give you a TMR effect. And if you push more electrons, then the torque will be sufficient to force the magnetization to reorient in a specific direction. So this is what is commonly used nowadays, and this is extremely efficient technology in the last products which are using ST-TMR. And then we got around 2010 novel discoveries of effects. So spin orbit torques that I'm going to describe in this presentation, voltage control of magnetic anisotropy, which was also reported the switching by VCMA in 2010, I think. And then we have also some other concepts which relies on breaking magnetization into domains and to move them using the current. So this is the racetrack or skyrmion concepts, to write magnetization with light or to read it with light, and so on. But today I will focus only on spin orbit torques. Before that, let me just say one word about spin transfer torque, which is what is in production nowadays. So spin orbit torque is a two-terminal device. This is about the writing mechanisms. So in one case, we get a spin polarization current which will torque the layer. In the other case, we are going to get reflections of electrons which will torque against the free layer and end up with a switching. In terms of characteristic, what is important from spin transfer torque is that because it's a two-terminal, you need to be very careful. You need to separate well your read and your write operation. And you need also to make sure that because you are using a two-terminal, that your write operation is far enough from the breakdown. And these are the main challenges of STT-MRAM. STT-MRAM can be written very fast, typically nanosecond time scale, but if we want to write faster, we need to increase the voltage because the write voltage is 1/t. If we increase the write voltage, then we get close to the breakdown, and we severely affect the lifetime of the device. And if we want to read efficiently, then we need to put enough bias, and then we are going close to the write voltage. So there are all of this type of configuration to take into consideration, and which are important. So all of this to say that STT is extremely efficient, but in terms of device, it has to compromise between endurance and writing speed. So that means that typical writing latency for STT are going to be limited between 10 and 20 nanoseconds. So if we want to introduce MRAM in embedded memories, we need to provide something that can go faster. So it's alternative geometry to avoid the two-terminal configuration, or a faster writing mechanism, or both of them. And this is where spin orbit torques are coming into the game. So let me first introduce or describe briefly what is a spin orbit torque system. Spin orbit torque, first, it arises from a spin orbit coupling. So it's capability of some materials to convert a charge into a source of spin, and this even in the absence of magnetism. So this is spin orbit coupling, something that we find everywhere in nature, but which is dominant in heavy metals. Okay, heavy metals are typically platinum, tantalum, tungsten, these families. So there we have a strong spin orbit coupling, and we are going to generate strong spin orbit effect. Among them, we have two effects, one coming from the bulk, the spinol, one coming from the interface, Rashba. And there are some more effects that I don't describe here. So now you can see that if we have a material like this, which can generate a spin, if we put a ferromagnet on top of it, then we can start to manipulate the ferromagnet. Okay, so that means that here on top of the SOT layer, we want to put a ferromagnet, and typically we want to make it thin in order to go toward perpendicular magnetic anisotropy. And finally, this ferromagnet can be capped, and ideally we want to cap it with an oxide so that we can think of building an MTJ later. In terms of physics, I was mentioning there are two main effects. So one coming from the bulk, which is the spinol effect, and which is the capability of this material to separate electrons which are entering non-polarized into the material, and to separate them accordingly with their spin direction. So the left spin will go up, the right spin will go down, up and down will go out or in from the screen. Okay, so that means that at the end of the day, you are going to get a spin accumulation at your interface. And if you say that you have a plus and a minus in analogy with a charge, you are going to get a spin current. This spin current will torque the local magnetization, and the torque effect has this symmetry, which is M cross Y cross M. So this can be also written differently by more generically, but this is the typical form of the torque. And this torque results into an effective field, which is always perpendicular to the magnetization when we are considering out-of-plane magnetization. Then we have a second type of effect, which is coming from the interface, which is called the Rashba interaction, and which manifests as an effective field. So here it's also quite complex to describe what is Rashba, but it's basically a relativistic effect, which says that if you have an electron moving fast in electrical potential, it will experience a magnetic field. So when I say fast, we are meaning relativistic speed. And electrons at the Fermi level, so conduction electrons, are typically percentage of the Fermi speed, of the light speed. So that means that they experience a bit of this Rashba phenomena, and they experience this in plane field. So at the end of the day, this is manifesting as a field effect, which is going to be a field in the plane along the y direction, so perpendicular to the current direction. And this is a field that usually is much larger than what you can generate with Ørsted field. So more information you can find in these review papers, which are giving more details about the theory. When these papers are more discussing about the revealing this effect. Okay, going in the wrong direction. And so just to finish to mention that this feel like an anti-damping torques, because at the end of the day, at the beginning, we got a lot of controversy regarding what is the origin of this effect. And this has generated a lot of debates, but nowadays the consensus is more or less like in this picture. But just to mention that spinel effect can generate a field-like interaction, and Rashba interaction can generate anti-damping torque effect. So at the end of the day, it's always a bit difficult, but the common picture is this one, the one which is accepted. And just to mention also that this field-like and anti-damping depends, of course, on the materials that we are using. And what is typically reported is that these effects are defined as positive when we are using certain type of materials. For example, platinum, palladium, gold are positive effect, while tantalum, tungsten, iridium are negative effect. Okay, so now we know that we have some key elements in our system, and basically next step is first to know them a bit more and to define what is important if we want to now think not only in revealing the physics but optimizing a device. Okay. And so the metric for SOT is called the spinel angle. So it's the ratio between the spin current which is created compared to the charge current that is injected. And this is going to define the spinel angle. It's important to notice that in the case of SOT materials, the spinel angle can be larger than 1. So which makes it also quite attractive in order to generate more efficiency. And this is typically what you're going to find in topological insulator materials. So this is the formula for the spinel angle. And what you're going to do is you can characterize different type of materials. You're going to define a spin diffusion length, okay? And you're going to define a SOT efficiency, so a spinel angle. This is going to tell you which type of material you would like to use. And if we look at what is tabulated in the literature, the tungsten is the most interesting material in terms of what is immediately available in a standard fab for fabricating MRAM. And that if we look to the future, topological insulators may be of interest because they possess much larger spinel angles. Okay. So from this, now we have also what I discussed, a spin diffusion length. So that means that we are working with materials which have a bulk effect and they are relatively thin. So they need a certain amount of bulk before being enough efficient. So this is characterized by this spin diffusion length, which is typically in our materials in the order of 2 to 3 nanometers. And that tells you that typically, if you measure your spinel angle as a function of the thickness of your material, that tells you where you are going to be optimum. Because at this point, all the charge that you're going to inject are going to contribute to the switching. If you increase more the thickness, many of the charges that you inject are not going to contribute to the switching. So it's better to be placed at this point. Okay. And so this is the way we are going to optimize the writing current. Just to mention that the development also depends on some type of materials, and that can be also a tricky operation. And if I take the case of the tungsten has 2 phases, alpha and beta. If it's alpha, then it's low spinal angle, but good conductivity. If it's beta, it's large spinal angle, but not so good conductivity. And the beta phase, which is of interest for us, is coming only below 4 nanometers. So all of these are also other parameters in terms of stack development to consider for optimizing. And to finish, it's good to optimize your SOT material, but you have to think that on top of this, you're going to get ferromagnetic materials, and that they need to keep their properties which are of interest to define a memory. And so there is a lot of material and stack engineering to perform in order to have a free layer that is enough anisotrope, which has enough retention. You have to take care of interfaces which can affect your efficiency in terms of spin transmission at the interfaces, and create also intermixing with heating. So there are many parameters. So from big picture SOT, you just play with few parameters in terms of thickness and material, but this has a lot of consequences on everything else. So this is also what has to be conducted with care. And just to finish on this part, I want to mention that there are different methods to characterize spin orbit torques, strengths, also to characterize the ferromagnetic properties. But and these are the harmonic hole voltage method that I developed in the past, the spin transfer FMR, which is also very useful because then you get frequency dependent effects, so you can get anisotropy, MS, and so on. And then you have also optical through MOC, which is basically a combination of AC and MOC effect, which allows you to quantify spin orbit torques. Okay, so this is to say what are the three main techniques. Nowadays, most of the people are using these two techniques, which are the simplest to implement. And what I want to tell you here is that it's very important to take the time to read correctly all the literature related to this, because at the end of the day, each of these techniques has also other effects which are contributing to the signals, and that I consider as an artifact because they are not the ones that we want to extract. And they are going to modify basically what you are characterizing, and they can mislead you on the amplitude of the effects that you are discovering. And just to give you an example, in harmonic hole voltage measurements, depending on the fact that you correctly took into account Joule heating effects that are relatively easy to characterize, but has to be taken into account. If you characterize a tantalum, a cobalt iron boron system, depending on the condition, you can find one or you can find three. And so you can see that this has a major impact later on your characterization. Okay. So now let's move to the second part, which is that we know that we have spin orbiter. We know that they can help to switch, but let's see a bit more about the switching. So switching, and in the following, I'm mostly going to focus on out-of-plane magnetized system. In-plane system are slightly different. So the first thing in out-of-plane magnetic system, and this is what you can see in this graphic, is that we need the assistance of an external field. So if we don't apply any external field, then we have random switching. Now, if we apply a negative field, we see that we have this polarity. So here I show the magnetization as a function of SOT current or SOT voltage. And we see that if I apply the opposite field polarity, then I am switching my symmetry. Okay, so that means that my switching is bipolar, either with applied current or with in-plane field. And here I show the symmetries, which are depending on the spinal angle of your material. So depending if you are working with a tungsten or platinum-based system, basically. And which are going to tell you that for a certain combination of current and in-plane field, you are going to get one transition or the other transition. Okay, so now why do we have this need of assist from in-plane field? So this is written here, it's to break the symmetry. So let's see why we need to break the symmetry from macro spin approximation. So macro spin approximation is basically the description of a magnetic system assuming that all the spins are responding together. So we consider here only one spin, and we do not consider exchange in between the spins. If we consider exchange, then we are going toward micromagnetic simulation. What we can see in this graphic is the following. So on the left axis, I have the magnetization in the z direction. And on the x-axis, I have the time. And then we are computing this Landau-Lifshitz-Gilbert equation, which is giving the description of magnetization motion over time. So under a stimuli. Okay, and here in this equation has been added only the spinel effect written by this form. Okay. So what we can see, and first I would like you to focus on the black curve, okay, is that if we do not apply any external field, the magnetization is going to be exactly at 0 in terms of z and exactly at -1 in terms of y. So basically, this is the nature of physics. When you have a torque, magnetization wants to align with the torque to minimize the energy of the system. So that means now that because we have an out-of-plane magnetized system, if magnetization is in the plane, it does not know if it has to relax up or down. So at the end of the day, you will get a perturbation and your magnetization is going to relax in a random state. Now, if we apply a positive or negative field, you will see that your magnetization is going to be slightly in the plus z or the minus z direction. And this is simply because the in-plane field is going to add a torque in the plus or minus z direction, which will force the magnetization to find another equilibrium position in plus or minus z. And that means that if we relax the pulse, then the magnetization is going to relax in one state or the other one, which is going to be dictated by this plus or minus z component. And so that means that now if we have the right combination of magnetization starting point and in-plane field direction and current polarity, we are going to relax up or down, and we can obtain a deterministic switching. Okay, so this is the reason in the macrospin system of why we need to apply a BX field. Well, this was in the simplified picture, because now if we add, in addition to the anti-damping, the field-like component, then we see that we get crazy oscillations, and this independently of the damping and other parameters. This is simply because the field-like is like an in-plane field along the perpendicular, along the plane, and so this is acting as an excitation field, basically. And this drives a lot of oscillations, so that tells us also that if we have the Rashba interaction in a macrospin model, we should observe very strong precessional switching. So this is for the macrospin picture. Now let's look at the experiment. So first, experiment has been characterizing the critical switching as a function of time. And here what you can see is that you have typically two regimes. One which is thermally activated and which can be written by this type of equation, and one which is relatively intrinsic and which can be written in these interactions. So to obtain such type of curve, what we are doing is that we are measuring the switching probability as a function of voltage. So here, for each of the points, we make sure that we reset the magnetization in a given state, and we apply a stimuli. And we do that for n events, typically 1,000 events. And we look how many times we have been switching. And from that, we are drawing a switching distribution probability. We are taking the 50% distribution, and this is what we are plotting here. But I think you can already see it here. And here, the transition is sharp, it's fast, and it's not oscillating. And actually, if we look at the critical current as a function of inverse of time, we even see that in the intrinsic regime, we have a linear dependency. Again, I will not go into the details, but this is very important because if you take a macrospin approximation, in the intrinsic regime, it's not linear, it should be quadratic. Okay. And we can also clearly see that we have no oscillations, and the macrospin simulation are telling us that we should be oscillating. And we know that we have a field-like interaction. This is well characterized in experiments. So there is something wrong in the description of systems that we are giving. What I want also to say is that this type of characterization remains very important experimentally because we are going to define a critical current, and this has to be defined from intrinsic properties. So we need to switch fast in order to define it consistently. And we are going to define a slope, which is characterized by this Q factor, and which are going to be very useful later when we are going to do compact models of our device to predict properties when we are introducing them in a memory. Okay, so switching is apparently not following a macro spin model. And nowadays we know why. It's because so far I've been talking about two current-induced interactions, which are the spinel effect and the Rajba interaction, but we did not discuss the fact that there is a third interaction arising from spin-orbit coupling, which is static, so which is not dependent on the current. It's the Jablonski-Kimura interaction, DMI. And this DMI has two effects. The first one is to force magnetization when it's not homogeneous to reconfigure, okay? And to have, if we say of two domains separated by a domain wall, in PMI system, normally we have a block system, a block domain wall, and this DMI forces the magnetization to have a nail domain wall. Again, I will not go into the details, but this has a lot of impact on the dynamics of the domain wall and means that with spin-orbit torque, we can move the domain wall with or against electron flow. So this is really the SOT which is driving the domain wall motion and not the charge current itself. The second thing of DMI and consequence is that because we have a system which has a finite direction, we have again a break of symmetry. And this is, so I said DMI is not existing in a homogeneous system, but as soon as we break the symmetry of the system, then it starts to appear. And one of the consequences is that if you are working with a finite size, so basically a dot that we are going to use for memory, then we are going to see a canting of the magnetization on the edge. So because this magnetization is experiencing a DMI field. So this is what is recapped here. On the side, at zero external field, we have a canting. But what's happening is that if we are applying now an in-plane field, then we are going to reconfigure the magnetization and we are going to make one edge of the dot stronger and one edge of the dot weaker in terms of magnetic energy, because more in plane and more out of plane. And this is basically telling us, and this is demonstrated by micromagnetic simulation, this is telling us that basically we have a micromagnetic system where we have an edge nucleation followed by a domain wall propagation. And this is because of DMI. And so this was something which was said experimentally by simulation, and that later we have been demonstrating in synchrotron, doing spatial and time resolve experiments and confirming this hypothesis of DMI favoring a nucleation on the side of the wall of the dot, excuse me, and then a reversal completed by domain wall transport across the dot. And so this is what we have been doing in this experiment. Okay, so at the end of the day, what we have been learning here is that switching occurs by domain wall nucleation, which is followed by a domain wall transport driven by SOT, and that these typical processes, so they are set to scale down to 25 nanometers. So all of this, of course, depends a lot on the energies that you are going to consider on your system. What is the DMI value? What is the anisotropy, and so on. But typically, if we take the most standard system, which is platinum cobalt based, down to 25 nanometers, we should see effects which are dominated by nucleation and domain wall transport. I just want to say one more word stepping before the device realization is that later we have been able to realize spin orbit torque magnetic tunnel junction devices. And that gave us actually opportunity not to read by synchrotron methods, so basically photons, but to read electrically the signal, which is also more convenient because you don't need to go to a huge synchrotron and you can access much smaller dimensions also. So you lose the spatial resolution information, but you gain in terms of speed and in terms of insight of what you can get. And so here is a setup that we have been building with CTH. And what is important here is that you see the switching on the same device, which was operated by spin orbit torque or spin transfer torque. Okay. So what's happening? First, we see that spin transfer torque is a well-spreaded distribution probability over time. And this is related to the incubation time. So this is something that I forgot to mention initially, but in spin transfer torque, the two ferromagnets are in the same direction. And if you remember, I said that by nature, a torque does not exist if the torque and the magnetization are aligned together. So in STT, we are relying on the fact that magnetization must fluctuate, induced by temperature, for example, before the STT torque applies on the magnetization. In spin orbit torque, we say that we do not need to wait because the torque is perpendicular to the magnetization. So the torque should directly apply. And here we see that we have a relatively narrow switching distribution. So this is cumulation of 5,000 events. But we see that the T0 is actually not at 0 when we should expect it to be 0 because basically the torque is acting instantaneously. And now if we look at single events, not accumulated events, we see that actually we have a jitter. So basically the T0 varies and the delta T is relatively similar. And we see that if we increase the voltage applied on the SOT line, then of course we have a much narrower distribution of T0. The explanation behind this is actually also temperature. We have always temperature, which is local temperature, but also the one which is induced by the current. And what's happening is that we know that we are first reversing a domain, which is followed by a domain wall propagation. And so the temperature is acting on the anisotropy, the magnetization, saturation, and the exchange. And so this is going to give some fluctuation on when you are able to switch your first domain before giving propagation. And this is what is explaining this jitter that we are seeing here. So just to mention that temperature is also important even in the case of SOT, because this is going to have some effect on how fast we can nucleate and propagate a domain wall and how reliable we can do that. What is important is that all of these type of time resolved experiments are relatively complex to set up, and that all the experiments that I was describing before, which are what we call post-pulse measurements, so meaning that we send something and a few milliseconds after we look if the magnetization is reversed or not. The interpretation we get in terms of scaling 1/t and other interpretation we are taking from this type of laws are still holding. So what we are finding in the time resolved experiment gives us more rich information, but the big picture is still the same description. Okay, so now let's go toward how we are fabricating these devices. So for the fabrication, so basically here are the asset of SOT-MRAM technology. So basically we decouple the read and the write. So we have no read disturb. We have a spin torque which is perpendicular to the easy axis, so we have limited incubation time, and we can write very fast without degrading the device. Now we have also some challenges: how to write reliably the information, so field-free method, which type of metal we need to introduce, the MTJ performance, how we can design, but most of all, first, how we can manufacture this type of device, and how we can define. There are different challenges here that I'm going to describe. So how we are integrating the device is as follows. So here I'm talking about large-scale wafers, so typically 300 millimeter wafers, which are produced in fabs which are industrial compatible. So typically what we are doing is first that we have metal lines, which are going either to be used to address electrically the device from external source, or that are going to be interconnected with CMOS. Okay. On top of it, we are going to fabricate vias, which are going to access the device. At this stage, after the via, so we dig the holes, we refill with metal, and then what we do is we deposit the SOT MTJ stack, we do the annealing, and then we deposit a hard mask. So the hard mask is then patterned and is used to form the MTJ pillar. Okay. So here we have a first challenge is that when we are etching the device, we want to stop precisely on the SOT without pinching through, and we want to also go very straight, and we don't want a footing. So here we need to develop specific etch recipes, which we have been achieving. So basically STT is etching at 30 degrees. In SOT, we are etching at 0 degrees. And then we are monitoring thanks to endpoint control. We are monitoring where we are stopping and defining stop etch strategies. So this is something that IMEC or other industries are now mastering quite well with yields which are relatively interesting. So more than 90% of the device which are coming out without shorts. After fabricating the memory element, what we are doing is first an oxide refill. So we put oxide everywhere. We do a CMP, so chemical mechanical polishing step to flatten everything. And then we put the SOT hard mask in order to pattern the SOT channel. After patterning the SOT channel, then we complete with electrical connections, which are going to go for the access lines or to the pads for electrical testing. So at the end of the day, we end up with a device which is looking like this: two vias, a SOT channel, a MTJ and the intersection, and the possibility to write in the plane or to read the state of the device. And this is how it would like if you would consider putting it in an array. I mentioned that there are different, so you can fabricate this technology in plane or out of plane, okay? But in terms of scaling and other properties, we are more interested in doing out of plane, at least in some places. I mentioned also that there is a field-free switching solution that needs to be enabled. So there are different solutions which relies on breaking the symmetry by structural asymmetries, by introducing one more field, okay, which is coming from interface or which is coming from somewhere in the stack, by using specific material geometries, which are related to the crystal symmetries, or by hybriding the approach. So for example, combining STT and SOT using domain walls having string. Here is a benchmark table that I created. Of course, it's not all the details, but if we look realistically on what can be integrated nowadays in the fab, there are three main approaches: embedded magnet, which is a solution I propose, so to use the hard mask as a field generator, STT assist, or in-plane MTJ. This is what is nowadays mature enough to be produced like in industry. Regarding device performances, okay, a bit late, I think, but device performances, these are the typical metrics we are going to see from the SOT MTJ. So what is the resistance as a function of the size? What is the TMR as a function of the size? And then I mentioned in the introduction that there are different metrics related to the free layer and the reference layer, so the coercivity, the pinning, and the offset, and all of this can be measured as a function of size. What we can see is that if we are extracting the retention of our device versus size, this retention value, so delta, is dropping quite low. And this is basically because we are losing more and more volume and we are going toward a macrospin limit. So that means that there are some efforts to increase back the retention, because if we look in terms of application, we would like to be around 70 at the smallest dimension used for application. And this is because later we are going to operate with temperature. Okay, if we look in terms of writing performances, I mentioned that in the sub-nanosecond regime, we have intrinsic regime, which is linearly scaling. So these are measurements that we are making here with our typical devices, which are 160 nanometer SOT widths for a 60 nanometer MTJ. You can see that if we are rescaling the device width, which was the second generation basically, then of course we have less metal that is not used for the switching. And so we end up with linear switching of the device. excuse me, and we end up with reduced current switching. And you can see that using some simple model, we can see that we are able to correctly project on what should be the required current. And so if we scale to what is required for application, we see that the switching current at 1 nanosecond is still more than 200 microamps, which is insufficient for applications and calling for more efficient materials than tungsten-based devices. It's interesting to see also that on the same die, we can measure SOT and STT. We see that STT is actually much more efficient than SOT, but it's limited in time. And so if we go fast enough, then we are also quite efficient in terms of energy using SOT. And with the most up-to-date devices nowadays, we are reaching typically 100 femtojoule energy writing at 300 picoseconds. And finally, I was mentioning that we have also this type of jitters that has to be considered for performances. How reliable is the writing with distribution of the writing time and the writing length? But what is important is that on the same stack, we can process at the same time SOT and STT technologies. So we can go for high density application, for faster applications. So this is also offering interesting perspective. And the last word about the performances is that all of this is good to be able to switch a device, but you need also to be reliable, as I was mentioning. So do you have a tight distribution or not of your writing? What about the write error rate? So typical targets for MRAM are 1 to the -6. So we need to write 1 million times without error. So what's going to happen here? So these are studies which are not so often conducted. And we need, of course, to be endurant. And here I show measurements where the device has been cycled many times, 10 to the 11 or 10 to the 12th time without breaking down despite the severe stress that we are applying. But still, there are a lot of lacks of report on this type of errors, and this will be important to enable the technology later. One word to say that there are also in-plane systems which are existing, various reports about them. You can read these papers. The physics is quite similar, just the scales of the device and the switching time are not exactly the same. Okay, to finish, first I want to say that it's interesting to see that more and more companies and institute RTOs are active on the topic, and that more large-scale demonstrations are appearing in the literature with co-integration with CMOS. So I think this is quite important to see that there are more and more actors, because that will push this topic even further. But that what we can see from everyone is that there is a need to improve the write efficiency and the density. There are some recent work from IMEC which are showing that now you can create novel structures which are called hybrid free layers, which are basically going to couple a layer that has a good PMA with a reading layer, okay? And this has been a nice way to improve significantly the retention of the device towards the specs which are required for applications. So more than 70 at a 15 nanometer diameter, okay? And this even at 125 degrees. So this is very, very good news. Without major penalty, and so there are some tricks here, but without major penalty on the writing current. So this is also quite important message. There is also a need to think about the design, because a single cell is something, but then you need to see how you are going to implement that into a memory architecture. So first, SOT is a 5-terminal device, 3 terminals for the SOT, but you need also to consider the transistor selectors. Okay, so that makes 5 terminal, which is the same as SRAM. And that means that in terms of density, you don't have a huge gain. So there are some design work to show that you can reduce the amount of terminals. You can create high performance or high density devices, SOT devices, which are competing or which are much better than the SRAM in terms of density. You have to consider how you are going to route your signals, and all of this is going to have an impact on your architecture. So there are many things to consider, and this is really the work of designers and architects, which are going to combine compact model, digital design to technological optimization, performance power area designs, And then all of this is going to be combined together to make a macro memory, so to demonstrate an array. Just to mention two more words. One is about the fact that there are other effects like VCMA that I mentioned at the beginning, which is basically applying a voltage will modify the perpendicular magnetic anisotropy. That can create oscillations of the magnetization. But where it is interesting for us in SOT is that we can combine it to SOT. And that can be used basically to lower the energy of the free layer to switch. And this is something that we demonstrated that you can see here. So the device is gated under different values, and you can see that we are increasing or decreasing the writing energy. And you can see it also from this graphic with write error rates. It's also interesting because that means that you can think of designs where now you're going to have one SOT track with multiple MTJs. And this is actually quite interesting. And this was proposed by Toshiba and Professor Yoda. This is quite interesting to gain density. And we see that with 4 MTJ together, in terms of density, we are equal nearly to STT design. So this is a major idea in order to gain density. And you can also, instead of VCMA, you could also use STT, and then you can think of building this kind of NAND-like device, which was reported by the group of Wei-Sheng Zhao. So if you read this paper. The story for SOT is not only stopping there. It can be used also to diverse the use of the memory, not only to be a memory, but also to be used in novel computing. So in novel computing, there are many concepts, but SOT could be quite useful for what we call in-memory computing, analog in-memory computing for digital neural network inference hardware. So which are typically used to sort or to recognize an image or someone speaking or whatever. So here in this type of approach, what is key is to have a memory element, which is going to be used as a weight, not as a neuron. So a memory element that is very, very high resistance. And when we say very high, it's typically mega ohms, okay? And at the end of the day, if you look at non-volatile memories, there are very few of them which are able to achieve that. So if you take STT, of course, STT cannot write when it's very large resistances. If you take PCM, it's limited to below mega ohm. If you take OXRAM, similar, and then you have also a lot of fluctuation or variation of the reading element. And MTJs, well, they can be easily tuned in terms of resistance by the MGO barrier. It's simply you make it thicker. And the distribution of the values are quite tight. So that makes it actually quite interesting for being placed as a weight element. And here we are going to use the SOT to write the information simply. So this is just to show, and this has been evaluated, you can read more in these papers, that SOT is of interest for this type of computation. And we have even extended the work to have multi-pillars, which allows us to obtain multiple states, which at the end of the day is even more interesting for this type of computation. There are also other use of SOT to basically propagate a domain wall and to make logic operations. So here you have different concepts which are based on nucleating a magnetization using STT, transporting the domain wall by SOT, and the combination of domain wall are going to make a truth table, which is going to make a AND or NOR operation. You can have something quite similar, which was proposed by Zurich, and I see that I forgot to put the reference here. So by the Professor Gambardella, by the lab of Professor Gambardella, which is basically relying on deterministic switching induced by transition from in-plane to out-of-plane systems, and which allows to make this type of operations. And you have also novel effects or proposals which are more using the inverse spinel effect, so the capability of a material to create a charge depending on the orientation of the material, and which are giving rise to this meso magneto-electrical spin orbit coupling devices proposed by Intel, or one also coming from Spintech, which are ferroelectrical spin orbit coupled devices. Okay, So with this, I will stop here just by concluding that nowadays we are able to take the development and the understanding of spin orbit torques to make devices which are called SOT-MTJ and SOT-MRAMs, that we are able to integrate them with technologies which are compatible with front-end, so CMOS basically. We have developed a field-free manufacturable solution. We can switch very fast and with low power. So that makes the SOT-MRAM a technology which is promising solution for SRAM cache replacement. But of course, these are the first early demonstrations. So now there are many things to improve to move from the proof of concept to a real product. And for this, we need to work on improving the write efficiency, to improve the stack performances. We need to see more about the modeling design and how we can use these devices. And we need also more view on real demonstrators, which are going to feed us back with potential limits or benefit of this technology. And of course, spinning around this, as I was showing, there are some emerging areas of research like machine learning using this DNN, or probabilistic computing and Ising or so Ising computing. Cryocomputing is an area of interest. 2D materials is the future generation, maybe. So many things where a spin orbit is involved, and that will have impact on spin orbit torque based devices. So with this, I would like to thank you for your attention, and sorry for being a bit late on my talk. So if you have questions, I think we can open the discussion.
Okay, thank you so much, Kevin, for this wonderful overview. Actually, I thoroughly enjoyed. I'm sure it must be the same for all the other participants. So don't worry about the time. We all were with you all the time. So before we take the questions, I'd like to request you to stop sharing the screen for a second, and I request all of you to turn on your camera. Let's take a group photo, and then we will continue the interactions. Yeah. Okay. Okay. Oh, hello, Carlos. Good to see you. Okay, I request others to turn on the camera. I'm taking the photo now. Smile. Okay. All right. Now I request you to turn off your camera, and Kevin, please share your screen again. Thank you all. So kindly raise hand or write your question in case you want me to read it, or raise hands, then I take your questions. So I don't see right now, probably the talk was so clear. I have some query though. Like you have a quick slide where you summarized few approaches to achieve this field-free switching. I think 27, just a slide before. So could you tell a little bit more about it?
Yeah, so I had to go a bit faster on this, but so all of these are historical solutions which have been proposed. Okay. So if we look at structural asymmetries, so basically here you see what people have been doing is to create a wedge of one of the thickness of the ferromagnet or the oxide. At the end of the day, what this is making, and this is my own interpretation, is that you are creating a gradient of anisotropy, and that makes one spot easy to switch and the other not easy to switch. So that resulted in field-free switching, even though the initial interpretation was given from something else. So this was one way of achieving field-free switching. but if you look from applications, this is not very practical. You cannot make a local wedge for a device. Same concept was applied now by shaping the effect. So you put an angle between the torque and the magnetization, you put tips, and this is going to create a local nucleation, which will be followed by a domain wall propagation. So this was proven to be quite efficient, and I think it's an interesting solution. It was proposed by Spintech, so Mia Miron. In terms of fabrication, again, the lithography often is going to limit you in making the shape. So that's for the structural asymmetries. There is one new structural asymmetry that I will propose soon. So it's a paper that we submitted recently. So you will see about it soon, hopefully. Now there are the concept of having a field inside your stack somewhere. The first thing which was done is by the group of Professor Ono and Fukami, is to use antiferromagnet, which are going to create at the interface between antiferromagnet and ferromagnet an exchange bias field, so a local in-plane field, which is along the current, that can be set along the current direction. So this is actually quite interesting because you have at the same time a material that is able to produce a spinel effect and to produce an in-plane field. It has also some limitations in terms of materials that are available and can produce large spinel angle together in terms of reliability, because you can easily, if you hit a bit too much your device, then you're going to lose the exchange bias and you are going to lose the direction of the exchange bias. Similar here is to have a magnet below your SOT. And so either by coupling to the free layer or by a stray field, it's going to generate an in-plane field on the free layer. So this is working quite good. But then what's happening is that when you send a SOT current, first you have a lot of charge diluted into the magnet. So this is affecting the efficiency. And second, you are also going to create a torque on this magnet. And this will create dynamical effects, which are going to limit the reliability of the writing operation. Last is the solution that I proposed and patented in IMEC, is to use, so again, to pattern the SOT channel, we need to make a metallic hard mask. And I say, why not making this metallic hard mask also magnetic, simply? And here by shape, you're going to induce an easy axis along the current direction, and by stray field, you're going to have an in-plane field on the free layer. And this is what we are using and which is working very good. Then you have specific metals which have crystal symmetries, which are generating a torque, a spin torque, arising again from the SOT material, but in a different direction. So you can get at the same time a torque in the Y direction and in the Z. So it's a bit analog to having STT effect, except that it's coming from a non-magnetic material. And then I was mentioning hybrid approach, where you are going to combine different effects, and which will result in also controlling your device. So you have STT plus SOT. My opinion is more like it's STT assisted by SOT, but at the end of the day, it's really the combination of the two. So it's an hybrid mechanism. You can move a domain wall that you can transport by spin orbit torque back and forth, but you have the problematic of quenching enough well your domain wall at the edge of your device. And some recent demonstration on strain that was also changing the switching or inducing field-free switching.
Okay, thank you so much. I see some questions. Kamalika, please unmute on your camera and ask.
Hi, Kevin. Thank you. It was a very, very nice talk and learned a lot again. I have a very trivial question for your PMA-based SOT systems. You need to apply a magnetic field to break the symmetry, right? Mm-hmm. And on top of that, you also mentioned that you have a DMI at the interface. So my question is, does this DMI, in addition to this external field, would it destabilize the top free layer? I think it was 17 or 16, 17, 15, somewhere around there, I guess. Yeah, this one, yeah.
When you say destabilize the top free layer, you mean the rest of the stack?
The top layer. Mostly the intention for you was to also control the stray fields, right?
So it's more, yes, it's more the opposite, and this is something I cannot answer clearly. So the stray field itself is going to, it's not just a Z field, it has also some in-plane components. So if the question is there impact of the stray field on this, I don't know yet. It's quite complex. Now DMI is not going to really impact because we see it as a edge angle, but it's not generating a strong field on the rest of the stack.
But the reverse on the action on the DMI for the rest from the rest of the top stack can be, how, does it negate it, or because do you need for the reversal mechanisms these occurrences of skyrmions, or the DMI will clearly create this in such a configuration of material stacks you have? So
I'm not sure exactly to understand the question, but regarding skyrmions and so on, so here we are working with large anisotropies, so it's unlikely that we are going to generate intermediate skyrmion. It's going to be a domain wall most of the time.
Okay.
And the second thing is that there will be limited or weak inference with the stray field. So the stray field is going to perturb the full dot itself. But not exactly it will just add to the DMI.
Okay, yeah, thanks.
Okay, thank you, Ramalika. Luis, please unmute, turn on your camera, ask your question.
Hello, Kevin. Thank you for your talk. It's a interesting talk. I would like to know that in every SOT structure or SOT-MRAM structure that I see is an inverted structure. You use your free layer at the bottom and your reference layer at the top. I suppose this is because the type of chip in which you are building your structure. But any chance to put the free layer on top?
So yeah, good question. So actually, we do take this approach because it's much easier to fabricate. What you do not see, or that you actually see but often do not realize, so this is a typical approach, or I'm going to take this, okay, is that in addition to this, you have to form the MTJ. Okay, you have also a hard mask. Okay, I'm going to put with the right colors. Now, if you say that you want to fabricate it this way, okay, that means that you will need to put a hard mask to fabricate your device. So the question is now, so and here you would still have a bottom electrode. So now the question is, how are you going to interface your SOT with your free layer, knowing that we are very sensitive to the free layer? And second, imagine you remove your hard mask. How are you going to have this in contact with being, you always have a topology, okay? So how are you going to do that? So these are interesting things to try to resolve, but it's in terms of fabrication, very complex to fabricate. So there are possibilities. Now it would be to evaluate if we have a gain by doing this or not. Is it clear enough?
Thank you.
And it's true that, just to say one more word about this, STT is always using this configuration, and these are because typically for two main reasons. The first one is there is more TMR, and also the reference layer and the hard layer, they have a different texture, as I was mentioning. And so basically the stress that they imply on the free layer is degrading a bit the TMR and the free layer properties. So that's one thing. The second thing is that because you are in this configuration, when you are doing your etching, you can etch, and what is surrounding the bottom electrode here is oxide. So that means that the more you etch, the less you have possibilities of metal deposition on your side walls. And so this brings you to a better yield of device. And that's why here we have been really reworking the etch process in order, because we are stopping on the metal, so that can also create a short, in order to limit the total amount of shorts, so the yield of the wafer in terms of functional devices.
Okay.
Okay, thanks.
Thank you, Louis. Thank you, Kevin. I think it's about time. As I understand, Kevin has to go to pick his kid. It's almost 5. So I request you to stop sharing your screen. Oh, Carlos has a question we can take. Carlos, are you there?
Yeah, hi. Thank you, Kevin, for the nice talk. Just a short question. I saw in one of your slides, I mean, a lot of things, beautiful things I try to follow. In one of your slides, you mentioned that iridium have a negative spin orbitor. You measure that, or is a reference? Because we measure iridium by spin pumping, we find the same sign of platinum. So.
Okay, so I think this is a historical slide, so it's here. And to my knowledge, it was a negative, but there are very few reports about it.
Okay, because we measure recently, we find the sign of platinum. So that's because I was wondering.
Okay. Okay, no, but then I will correct that once you have published. And and the second thing is there are very few studies on iridium, because it's quite expensive. It's also quite resistive, so not very well adapted for SOT. But I thought the initial reports were saying negative. Okay, I will correct that. Like the iridium manganese is negative, for example.
Yeah, I don't remember, but that could be, yeah, that could be.
But I measured iridium manganese.
Okay, okay, I didn't. Okay, thank you.
Okay, thanks, Carlos. Kevin, can you please stop sharing your screen? I like to share my screen.
Yeah, sure.
Yes, so I'd like to present a small token of appreciation from our team. I hope you can see the screen.
Yes.
So before I read it, I'd like to announce about the next week's talk. Next week, Thursday, we will have the lecture by Professor Claudia Felser from Germany, and I hope you can all join, and we continue this seminar activity. So for today, on behalf of my whole team, I'd like to thank you, Kevin, for your excellent talk. And on behalf of our team, I'd like to present this small digital memento. I will send it to you by email. I will read it. W2S Seminar Webinar Series on Spintronics, National Institute of Science, Education and Research, NISER, Bhubaneswar, India. Takes pleasure in presenting this plaque to Professor Kevin GARELLO from SpinTech in Grenoble, France, in recognition and appreciation for being a very valuable speaker to give a lecture on SOT-MRAM basics, technological implementation, and perspectives. Thank you so much, Kevin, for your very nice lecture. We all enjoyed, and I hope one day you can come to India and to visit our institute. I would be very happy to host you. And yeah, well, let's keep that spirit, and please all stay healthy. And next week we meet Indian time 8 p.m. Thank you all. Have a nice day or nice evening, and see you next week. Thank you. Bye-bye.
Thank you also.
Bye.
And have also a nice evening. It will be a pleasure to come to India too.
Yes,
to visit your country.
Very nice. All right. See you.
Bye.
Bye-bye. Bye all.